Thanks very much. Is the sound on okay? Hello, everybody. I'm really delighted to be here. I had a great time at the NDR conference last year in Iași, so it's great to get back to Romania again. I'm from Dublin, at the Technological University Dublin, and I'm an academic by background, so I have a tendency to teach. And today's talk is probably going to be more it is going to be more a tutorial introduction, kind of comprehensive, but hopefully clear introduction to backpropagation, than necessarily a presentation of new amazing results. So my goal for the talk today is that when you walk out that door at the end of the day, you'll have a really clear understanding of the backpropagation algorithm in detail, its relationship to the chain rule in calculus and what that rule is, and also why there's problems in relation to the vanishing gradient of merges, and how, for example, shifting or changing the activation functions that a neuron uses to a ReLU, or rectified linear function, helps with that. Okay, so they're the types of topics I want to cover with you today. Okay, so I hope it's of use to you. However, I'm going to try and start from the ground up. So I'm going to begin by really a 101 on neural networks, get down to those building blocks, and then we can get into the algorithm in more detail. Neural networks are part of machine learning, and machine learning is fundamentally about learning functions from data. So the first concept we need to clarify is what we mean by the term function. And that's actually a relatively simple concept. A function is simply a mapping from a set of inputs to an output. And we use functions all the time. So you'll have done addition or arithmetic in high school. A clear example of a function would be the addition function or the summation function. So for example, the summation function would map the input values 2, 5, and 4 to the output value 11. That's a very straightforward function. When we're talking about neural networks, there's a particular function we're very interested in, and that's called a weighted sum function. So a weighted sum function it's very useful, and it's used in lots of places in computer science, but it's actually a very simple function. Basically, the function, we have a set of weights that are predefined. They're actually the things we're going to be learning from our data, and then we take a set of values, a set of inputs. And all a weighted sum function does is, for each input value it receives, it has a corresponding weight. It multiplies the input by the weight and sums the results. That's why it's a weighted sum. Okay? Very straightforward, hopefully. By the way, as I go through this talk, if I lose you on a slide, if you have a clarification question, feel free to ask it at that point. If you have a more general, because I'd like you to stay with the narrative. If you have a more general question that isn't a clarification question, then hold that off until afterwards, because I don't want to go over time. And we can discuss the more general questions at the end if we have time. So we have a weighted sum function here, very straightforward, and that's the basic building block of our neural networks. The next function we need to be aware of is what we call the activation function. It's also referred to as the transfer function in neural network literature. And there's been a range of activation functions used in neural networks in their history. The early types of neural networks use this transfer function here. It's a threshold function. Now, all the transfer function does, or the activation function does, is it's going to take the output of our weighted sum function and apply a nonlinear mapping to it. It's important that it's nonlinear because by introducing a nonlinearity into our calculations, we allow the network to learn a nonlinear function. Okay? So the simplest type of nonlinearity would just be a threshold where we say, right, if the weighted sum value is above a certain threshold, I'm going to output a 1. If it's below that threshold, I'll output a 0. Very simple threshold function. And those were the early threshold functions. So if you're reading literature on this, McCulloch and Pitts, their type of neurons, their early neurons use that threshold function. The problem with those types of functions is when we are using backpropagation to train a neural network, we're essentially using a rule from calculus, from differentiation, called the chain rule, and I'll explain that later on. But for that reason, we want it's useful if our activation functions are differentiable, okay? So we want, that means that they should be continuous. I won't get into too much detail there, but essentially there's a discontinuity here in a threshold function. There's a gap where the gradient is kind of infinite. So we can't use that for backpropagation. And that's why in the 80s, when the backpropagation algorithm was first introduced, people switched over from these threshold functions to logistic and tanh functions. The reason for that is that these functions have a very easy derivative. And I'll explain the derivative of the logistic later. All right. The downside of these is actually, when we're talking about feed-forward networks and a lot of networks, the derivative of the logistic function, for example, has a maximum value of 0.25. And that's where a problem called the vanishing gradient problem arises. And I'll talk about that a bit later on, but it's just if you've heard of those terms, I'll explain those to you later, where they come from. But that is why more recently, neural networks have switched over to what we call a rectified linear function. So a rectified linear function, this is an activation function. They all do, by the way, again, all of these things do the same thing. They're just taking our weighted sum value and changing it in some way, in a nonlinear manner. The nice thing about a rectified linear function is it's a function that is as close as we can get to linear, which means that it's relatively easy to learn a linear function, okay? So keeping our activation function linear helps us with our learning process, but it still adds a little bit of nonlinearity to it, okay? So that means we can still learn nonlinear functions while still staying as close as we can to linear, which helps us during training, okay? So more recently, there's versions of the rectified function that we use, okay, for our neurons. However, so just to put this in perspective then, those two simple building blocks, the idea of a weighted sum function and then an activation function of some type, defines the building block of a neural network, a neuron. So here we have our weighted sum function, which takes a set of inputs. This is a vector of describing a particular example. These weights, which we're going to have to learn during training and which are fixed during inference when we're applying the network. And we just take that weighted sum, the output of that weighted sum, and push it through another function, called, in this case, I'm using the example of the logistic activation function, to give us the activation for the neuron. And those two operations together, a weighted sum followed by the activation, defines a neuron. Okay? So all the neurons all our neurons back from McCulloch and Pitts forward have those two components in them. We can represent, we sometimes like to draw neural networks, and we can represent a neuron using a directed acyclical graph, where we have a set of edges. Each edge coming into the neuron carries an input into the weight, okay, into the weighted sum function. Each edge is labeled with the weight that's applied, the corresponding weight applied to that input. The summation sign here, I'm using that to represent the weighted sum function. And the phi symbol here, I'm using that to denote or represent the activation function. So all we're doing here is the exact same as on the previous slide. We take in this set of inputs, we multiply each input by a weight, we sum the results of those multiplications, and push the result through a nonlinear activation function, and that gives us an activation out. That's our neuron. When we want to build a network, we simply add those neurons together, connect them together in interesting manners. And there's lots of different ways we can connect them together in a topology. What I'm doing here is, this is an example of a network. Each of the circles represents a neuron doing that weighted sum and activation. I want to highlight here the fact that neural networks don't have to be organized into layers, but typically they are. So here we have a neural network where I have an input layer on the left-hand side. Now, while we talk about those as neurons, we should really think of them as sensing neurons, because those neurons are just locations of memory where we present information to the network. They don't have weights associated with them. They don't do a transformation on what they receive as inputs. Okay? They're just the sensing neurons. We then have a sequence of layers. This is a standard feed-forward, fully connected network. We have a sequence of layers, and we make a distinction in the literature between the output layer, which are the neurons in the last layer of the network that we can see the outputs from, and the hidden layers, okay? And when we talk about a deep network or the depth of the network, we can think about that in just counting the number of layers. Now, the question in relation to how many layers does it take to be deep, I would argue that a network with at least 2 hidden layers is deep. The reason I take that view is because there's a mathematical proof showing that if you have at least 3 layers of neurons, then you have a neural network as a universal approximator for functions. That's why I take it at that depth. In reality, a lot of the time when we talk about the fact that the number of layers define the depth of a network, in reality what we really mean is each layer has a weight matrix associated with it. Okay? So for example, this first hidden layer, each of the neurons in that layer has a set of edges coming into it, and each of those edges has a weight associated with it. That means that one of the reasons why we can use GPUs is we can represent that set of weights on those edges in a matrix of weights. And that means there's a weight matrix here, there's a weight matrix here, a weight matrix here, and a weight matrix here. So there's 4 weight matrices that we have to learn when we're training this network. And that means that we have a depth of 4 when we're doing backpropagation. Now, if we were training an individual neuron, okay, kind of an intuitive way, we want to learn the weights for the network. So an intuitive way of understanding how we can learn the weights for a single neuron is this way, that if we take the output of the neuron and we realize it's too large, then we want to decrease the output of the neuron for that example. And we can do that relatively straightforward. We just look at all of the inputs in that input vector that were positive, and we reduce the weights on those inputs. And for all the input vector, or all the inputs in that input vector that were negative, we increase the weights. And by doing that, that means that the next time that neuron sees that input vector, its output will be reduced in relation to that input vector. The mapping it made from that set of input, from the set of inputs to the output, will have changed so as to reduce the output. On the other hand, if the output of the neuron is too small, then we just do the opposite, and that will increase the mapping. Okay? So intuitively, that's all we need to do to train a neuron. The problem for us when we're training a neural network is that while we can use that type of an intuitive explanation to understand how to train the neurons in the output layer, when we have multiple hidden layers, we don't know for a neuron in a hidden layer whether the output activation of that neuron was too large or too small. So we don't know how to output the weights. What we have to do is we have to, in a way, take the output of the network, the error at the output of the network, and share it back through the neurons in the network. Essentially, it's known as credit assignment. It's a negative kind of credit. It's basically how much are you to blame for the network error, okay, or blame assignment. And that's what the backpropagation algorithm is going to do for us. It's going to share back the network error to each of the neurons, so that for each neuron, we'll have an estimate of how much error it contributed to the network, and then we can use that estimate to update the weights of that neuron, okay? Now, if you look at the literature about backpropagation, if you look at it carefully, you'll notice that different books actually treat it in 2 different ways. Some books discuss it as just a solution to the credit assignment problem. And other books talk about it as a solution to the credit assignment problem plus a weight update rule. And I think it's useful to understand that distinction, because typically what we do is most of the text that you look at will explain it with the weight update rule and assume that you're using gradient descent. But you can change the weight update rule to other aspects. I should say, in my original ambition for this talk, I was hoping to cover gradient descent with you as well. But for 30 minutes, I'm probably going to go over time anyway. So I ended up deleting half the talk about an hour and a half ago. Okay, just didn't have enough time. But I'll try and cover the weight update rule as well today for this. So just be aware, if you're reading about backpropagation, understand that it might just be a solution to the credit assignment problem you're looking at, or it could be that plus a weight update rule factored in. And we can change the weight update rules that we use. Now, at a very high level, the backpropagation algorithm, we have our network topology, we've defined it in some way. So now we want to train the network. And we start off by just guessing initial weights. The initial weights of a network are really important And there's lots of different, there's lots of research done on how we should guess those initial weights. Okay, and if you want some references, you could look up Larotte initialization. But for now, I'm just going to say we're guessing initial weights, and we generally keep them quite small. Okay, and that's a whole other discussion about regularizing a function. But for now, we'll just stay with guessed initial weights. And then what do we do? So once we have a network that has initial weights in it, we can apply that network to examples in the data set. Obviously, it's not going to be a very good network to start with, but we're going to use the error of the network to iteratively update the weights so that it gets better. And we do that in 2 steps. The first is that we share back or backpropagate the blame of the error to each of the neurons. And then, I want to emphasize that work to each of the neurons. So we're going to assign blame to each neuron, and then we're going to use the blame we assign to each neuron to update the weights associated with that neuron. So that means that the error we assign to a neuron can be used to update multiple weights. All right? And that will become clearer or a bit more important when we talk later through some of the later slides. And we keep doing that until the network performance is good enough, and then we return the model. We we freeze the weights. Now, the fundamental principle of the backpropagation algorithm in adjusting the weights is that each weight in the network should be updated in proportion to the sensitivity of the overall error of the network to changes in that weight. Okay? So we're going to change it in relation to the sensitivity of the overall error of the network to changes in that weight. That can also be written as the rate of change of the error of the network with respect to small changes in a weight. And that's why we're going to start seeing some terms that are from calculus. So that term there represents the partial derivative of the error of the network with respect to small changes in the weight between neuron I and K. Okay? And what we need to do to change the weights is figure out how to calculate that term here. That term by itself is going to be, directly calculating that is going to be difficult. So what we're going to do, and what backpropagation does, is it decomposes that error term into 3 terms. And it does that using the chain rule. Once we have that term calculated, then the actual weight update rule that we use, and I'm going to explain to you in the next few slides how we calculate that term, is simply this. We just say, right, the weight at training iteration t between I and k, okay, is changed into this weight here after that training iteration by adding to it the sensitivity of the error of the network with respect to that weight multiplied by a scaling factor, a learning rate. Okay, I won't have time to explain that, but we just don't want to make very big changes to the weights at any time, so we typically scale them down before we update them. Okay. But the key thing I want you to understand is, so we want to update the weights in relation to the rate of change of the error of the network to changes in that weight. So we need to think about how does the change in a weight affect the error of the network. And it does it through 3 steps. When we change a weight, it changes the weighted sum of the neuron that it's on the input to. By changing the weighted sum of the neuron, we change what's the input to the activation function, and that's going to change what's the output of that activation function. So that changes the output of the neuron. And then the output of the activation neuron is passed on to later neurons in the network, and it's going to change all the downstream neurons' activations. Okay? So there's 3 elements that are affected when we change a weight. And what we need to do when we're calculating the rate of change of the error of the network with respect to a change in the weight is we need to understand how to calculate those 3 elements, the effect they have. Okay? So, here we go to a little bit of calculus. So the chain rule in calculus, which is basically the fundamental component in the backpropagation algorithm, it specifies how to calculate the derivative of a composite function. So a composite function is a function that takes as its input the output of another function. Okay? So for example, here I have a function g, and it takes as input the output of the function z, which takes as input the input x. Okay? So that there is a composite function that is the composition of g and z put together. And what the chain rule tells us, it tells us how to calculate the derivative of g with respect to the input to Z. Okay. So, and we just do that by decomposing this term here into the product of these two terms. So this is the rate of change of G with respect to the input it receives, multiplied by the rate of change of Z with respect to the input it receives. And we're going to do exactly that decomposition to figure out how do we calculate the rate of change of the network with respect to a weight. And we're going to do that because we're going to end up with the three terms, each describing the three elements on the previous slides. Okay? And this is it. So, the rate of change of the error of the network with respect to a weight in the network. Well, that's equal to the rate of change of the weight of Z represents the weighted sum in the neuron. Okay? So this is the rate of change of the weighted sum of the neuron with respect to the weight. Okay? And then what we do is we multiply that by the rate of change of the activation of that neuron, the output of the neuron, with respect to the weighted sum, which will have been changed by changing the weight. And then what we do is we have this term here, which represents how the error of the network changes as we change the output of the neuron that the weight affects. All right? So this is decomposing that difficult term into three easier terms to calculate. And what I hope in the next 9 minutes I will get across to you is how easy these three terms are to calculate. They're very simple to calculate. They actually, you'll be surprised, hopefully. So, backpropagation is an efficient way of calculating those terms. Now, it's a two-stage algorithm. The first stage is a forward pass. So we present an input vector to the network, and we let that vector pass through until we get an output. What I'd really like to emphasize here is often when people think about backpropagation, they think that's all that really happens in the forward pass. And they put most of their focus on understanding how the backward pass works, which I'll talk about in a second. But what I want to emphasize here is there's a lot of work done in the forward pass that makes the backward pass much easier. This is where the efficiency comes in. So when we do the forward pass, we store, it's like dynamic programming, okay? We store for each neuron in the network the weighted sum of that neuron and its activation. Okay? And what you're going to find is, if I jump back a second, that term there, for example, is just going to end up being one of those activations that are calculated in the forward pass. This term here is going to end up being, we simply plug the Z value that we calculated for a neuron in the forward pass into the derivative of its activation function, which we'll know from looking it up in a book. Okay? That will give us that term there. And this one here, I'm going to explain how we calculate that for neurons in a second. Okay? But just remember, those two terms there just become scalar values that are easy to calculate once the forward pass is done. Okay? And that's why these values are stored, to make those numbers easy to calculate. Now, when we propagate forward through the network, just as I described earlier how a neuron works, this is just taking the activations from previous neurons. So this is a neuron somewhere in the middle of a network. It gets activations from previous neurons. Each of them have a weight applied to it. We calculate a weighted sum over them. I'm representing that weighted sum by the term ZK. And that ZK value, the weighted sum, goes into a nonlinear activation function, and that's the activation that goes forward. Okay? And we're going to store that value and that value for each neuron in the forward pass. Now, we get to the backward pass. And there's two types of error gradients that it's important to distinguish between. So the first is this delta. These are the error gradients that the backpropagation algorithm actually backpropagates. So the delta for each neuron, there's one delta for each neuron. That is the rate of change of the error of the network with respect to the weighted sum. So it's not with respect to changes in the weight, it's respected to changes in the weighted sum of the neuron. Okay? And there's one of those for each neuron. Then what we need to do to update the weights is we're going to take that delta term and modify it by multiplying it by another term to get the error gradient of the network with respect to changes in the weights. We use this second error gradient to update the weights, and this first error gradient is part of the calculations of second error gradient, but these are the error gradients that the backprop algorithm actually backpropagates. It's backpropagating the error with the rate of change of the error with respect to the weighted sums. So, going back to our equation of the chain rule, which decomposes the rate of change of the error of the network with respect to the weight, these two terms here are the delta term for a neuron. So that is going to be the rate of change of the error with respect to the output, the activation of the neuron, and this is the rate of change of the activation with respect to the weighted sum. So the delta term here is the rate of change of the error with respect to the weighted sum. This term over here is what we're going to use to update the weights. That's the other error gradient. And to get that, we take this delta k and we just multiply it by this other term here, which is going to be the rate of change of the weighted sum with respect to changes in the weight. It turns out that that's really easy to calculate because the weighted sum, that's just going to reduce to being the activation that that weight was applied to, which we'll have stored in the forward pass. Okay? So that just becomes the activation that we got from the neuron that WIK was applied to. All right. So let's focus, I'll come back to that. I'm going to talk about these two here for the moment, and in particular this side. I should say, yeah. What I'm showing you here is, this is the backpropagation of the deltas. And what I want you to understand is, you'll notice that so there's a delta for each neuron, okay? That's the rate of change of the error of the network with respect to the weighted sum of the neuron. You'll see that they're getting smaller as we go back. And that's what we refer to as the vanishing gradient problems. When we talk about vanishing gradient, it just means these are the gradients that are vanishing, those delta gradients. The reason why that's a problem is because if we update the weights in proportion to these terms, then these early weights in the network are going to get updated very slowly compared to the weights here. And a neural network generally works by these later neurons learn to build a solution by building on top of the solutions that the earlier neurons have learned. Okay? Because we're learning a hierarchical representation of data. And if we don't learn these early, if we learn these early representations very slowly, then the network's going to train very slowly. And the deeper the network gets, the larger this effect of the gradient getting smaller. And the reason it's going to get smaller is because this term here, for example, if we use a logistic function, that term here is going to have a maximum value of 0.25, okay, for a logistic function. And that means that every time we go back through a layer, the gradients get multiplied by a maximum of 0.25, and that's why they get smaller. And that's why we have vanishing gradients. And that's why changing to a ReLU, which doesn't have that problem with a maximum value of 0.25, can help with vanishing gradients. Now, here what we're doing is calculating the deltas, or backpropagating the deltas through neurons in the network. And there's two different ways we calculate it, depending on whether the neuron is in the output layer or in the hidden layer. Okay? So in the output layer, and what I really want you to see is this side here is the same for both of them. Okay? In both of these, we just take the rate of change of the error with respect to the activation of the neuron and multiply it by this term here, the rate of change of the activation with respect to the weighted sum. That box is the same as that box. That doesn't change irrespective of which layer we're in. I'm going to explain to you how we calculate that term here in a second. What I want you to focus on over here is this calculation, which is how the rate of change of the error of the network with respect to an activation of a neuron is calculated. This varies depending on whether in the output or the hidden layer. At the output layer, it's very straightforward. We simply take the difference between TK represents what the data set tells us is the target output for that neuron K. Okay? And AK is the activation of neuron K for this input. So we look at the difference between those, and that gives us the rate of change of the error with respect to changes in AK. And the reason why this subtraction, it's okay to think about this subtraction as a rate of change, well, that's because if we have a big difference between what the data set tells us and what the activation is, well, that means that we can change the error of the network very quickly by changing the activation, because there's a large error, so we can reduce it very quickly. If we have a small difference, then we can't reduce it as fast because the biggest difference we can make to the error of the network is quite small. So that's why we can consider that term there as a rate of change. Now, this calculation changes slightly. We end up with the same term, but it changes slightly if we're in a hidden neuron. What we do here is we're going to take the deltas from each of the neurons that are that this neuron feeds forward to, and multiplies each of those deltas. Again, it's another weighted sum calculation, but this time going backwards. We multiply each of the deltas by the weight that neuron, so neuron L would have received an activation from this neuron and would have applied this weight to it, okay, on the forward pass. In the backward pass, we take the delta for neuron L and multiply it by the same weight. And we sum them together. And that gives us the rate of change of the error of the network with respect to changes in the output of this neuron. In effect, it's how did the output of this neuron affect the downstream neurons. And it would have done that in terms of the amount of weight that those neurons put on the output of the network, of the neuron. Okay, so those two calculations are relatively straightforward. It's a subtraction or a weighted sum. And now all we're going to do is we're going to multiply that term here by this other term, which might look a little weird because it's a partial derivative. But how this calculation works will depend on the activation function we use. But generally, it's going to be the same. We take the derivative of the activation function. Now, the logistic function has a very easy derivative. Okay, so if I take the derivative of the logistic function with respect to z, that's just the value of the logistic function given z multiplied by 1 minus the logistic function when it's given z as an input. That is the derivative, okay? We'll just take that from a book. We won't derive it. To show you what that looks like, we can graph that value here. So what I have here is, in this image, I've taken an input values from minus 10 to 10. The dashed line up here, going along there, shows you the output of the logistic function as we change the input z to it. The full line here tells us, or plots, the derivative of the logistic function as we change the input z to it. What you'll see is, sorry, over here where the logistic function is flat, there's little or no change in the derivative. It's 0. Okay, it's saturated. As the logistic function moves up and it gets steep, then the rate of change starts getting steeper. It gets maximum around here, and then it starts to drop off. And the max value there of 0.25, okay, that's the maximum value this term can take when we use a logistic activation function. And that's why the gradients are always going to get smaller as we go back through the network when we use a logistic function. Because every time we backpropagate, we're going to multiply by a maximum value of 0.25, and that's why we get vanishing gradients. And that's one of the reasons why I'm explaining a backpropagation algorithm from the 80s, and deep learning took off, 2006, 2007. The vanishing gradient held it up for so long. Okay, so how am I doing time-wise? I've completely ignored my time. Apologies. So that gives us the chain rule of the backpropagation. So that's the deltas that are backpropagated. This term here just reduces to be the activation that the neuron received from the preceding neuron. Okay? So I hope, if we look at this slide, I hope that you now understand that those three terms are relatively easy to calculate. This is just going to be either the subtraction in the output layer or a weighted sum of the deltas in a hidden layer. This term here is we plug the z value for the neuron that we stored in the forward pass into the equation for the derivative of the activation function, okay? And that gives us that, just becomes a number, whatever value we get out. And this term here just reduces to aj because the weighted sum function, all of the terms, if we take the partial derivative of a weighted sum with respect to a given weight, all of the terms that aren't affected by that weight go to 0 because we're taking it, they don't change. So it actually ends up just being the activation that the weight was applied to. And we've stored that in the forward pass as well. So the forward pass gives us this term. It gives us the input to the function to calculate this term. And then this is the bit where you calculate by backpropagating the deltas. Now, I'm going to jump a couple of slides here, okay, to give you the summary slide, just so people don't, okay. One last example, just to see this working. If we have a neural network with just two neurons in it, neuron L and neuron K, okay, it's a very simple network. I've got an input to neuron K. Neuron K does its processing, and the output of neuron K gets passed into neuron L. And neuron L is the output, okay? That's all that's happening here. That's the first neuron doing its weighted sum, its nonlinearity. And this is the second neuron, weighted sum, nonlinearity. We have two weights here, okay? I'm going to skip that. I'm going to jump straight to this, okay? And this is the last slide or so. So if I want to backpropagate through that, well, if I take that first neuron L, I hope you can read this, I calculate the error with respect to the output by subtracting it. I multiply that by the derivative of the activation function, and that gives me my delta L. Okay? I then multiply the delta L by the derivative of the weighted sum with respect to the weight, which is AK, and that gives me my term that I use to update my weight. When I'm doing it that will allow me to update this weight here. If I need to update this weight here then, I'm going to use that delta L down here to calculate the sensitivity of the error of the network to the output of that neuron. And I do that by simply multiplying that delta L by the weight that was applied to the activation going forward. And what you'll see is this line here of 3 terms is the exact same as this line here of 3 terms, it's just the subscripts have changed. That's our chain rule, okay? We're doing the same thing each time. It's just that the calculation of this term here, that term, changes slightly whether we're in the input or the output layer. Okay, I should finish there because so hopefully that's given you a clear understanding of backpropagation, and thank you for your patience. So.
Thank you, John.
Okay.
Well, if there are any questions from the public while our next speaker prepares.
Excuse me, why are you still using the logistic functions? I mean, like, why don't you use the max 0z, which is easier to derive? It's either 0 or 1, and then you can have the limitation 0.5 that's gone. Why are you still using that? The other one?
I am using that because I wanted to have the simplest example I could to explain the vanishing gradient problem. Okay. So it's only to show why the vanishing gradient. I wouldn't use the logistic function these days, but for the purposes of illustrating where the problem arises from, that's why I use that there. Does that?
All right.
Yeah.
Yeah, thank you.